Hello everybody. So good morning to all of you. We are discussing our second part or second section of the stereochemistry, that is CHO-352 paper, and the title is Asymmetric synthesis. Our today's topic is asymmetric epoxidation. We know that, dear students, what is meant by epoxidation? So epoxidation reaction is the oxidation of carbon-carbon double bond, that is alkene, with the formation of three-membered ring with oxygen as a heteroatom. So this is a simple reaction, and for this we need an oxidizing agent and an alkene. But if we start with a simple alkene with a simple oxidizing agent such as hydrogen peroxide or MCPPA, then we are getting a simple epoxide. But if our target is to getting chiral epoxide, then we should think about chiral reagents and the catalyst. Okay, so today's our topic is asymmetric epoxidation. So asymmetric epoxidation can be done by number of ways, but there are basically two reagents that we are going to study today. The first one is Sharpless asymmetric epoxidation. Sharpless asymmetric epoxidation, and second one is manganese catalyzed Jacobson epoxidation reaction. Manganese catalyzed Jacobson epoxidation reaction. Okay, so let us start the first one, that is Sharpless asymmetric epoxidation. Sharpless. So what is this Sharpless? Sharpless is the name of scientist. Sharpless is the name of scientist who discovered this reaction. So what he has done, he has taken the allylic alcohol. Okay, so allylic alcohol are nothing but the hydroxy group is adjacent to the sp3 carbon, and this sp3 carbon is attached to the vinylic carbon, that is alkene. Okay, so this group, this moiety is called as allylic alcohol. So when allylic alcohol, they are treated with different reagents, then we are getting a chiral epoxide. Okay, so what he has done, or what three different reagents he has used, okay, so that we are going to see. So the first one is tertiary butyl hydroperoxide. Tertiary butyl hydroperoxide, the structure is like this: tertiary butyl OOH, tertiary butyl hydroperoxide reagent. So this reagent is nothing but a oxidizing reagent for the oxidation of this carbon-carbon double bond to the epoxide. Okay, then the second reagent is titanium tetraisopropoxide. Titanium tetraisopropoxide is a transition metal reagent, a transition metal catalyst. Okay, titanium is a transition metal, belongs to the D block. Okay, so that's why this is a transition metal catalyst. And the main important part which is giving, or which is able to deliver the chiral epoxide, is the diethyl tartarate. Is the reagent, it is nothing but diethyl tartarate, and this diethyl tartarate, the actual is, it is L plus diethyl tartarate. Okay, so L, D and L are the relative configuration of this diethyl tartarate. Plus and minus are the symbols used for their optical rotation. So this plus is dextrorotatory, so it is also written by small d sign. Okay, so this dextrorotatory L diethyl tartarate is used in this reaction, and this is a allylic alcohol. So when we are using plus diethyl tartarate, we are exclusively, or we are getting the one enantiomer in excess, that is alpha epoxide. So this oxygen atom in this epoxide ring, okay, so this epoxide basically is below the plane. Okay, and whatever the remaining substituents attached to this carbon-carbon double bond, they are remain as it is. So this is the main important part of this Sharpless asymmetric epoxidation, and we are getting 94% enantiomeric excess. Okay, we are not getting here the alcohol like this. We are not getting the alcohol like this. Okay, so this is the alpha epoxide and this is beta epoxide. We are getting exclusively this 94% enantiomeric excess with 85% yield. So that's why such epoxidation is known as Sharpless asymmetric epoxidation. Okay, Sharpless is the name of scientist who invented this process or this reaction. So that's why by the name of his or honored of this research or invention, This epoxidation reaction is known as Sharpless asymmetric epoxidation. So what is important here? So this is diethyl tartarate, which is nothing but a chiral catalyst. Diethyl tartarate is chiral catalyst is there, and due to this chiral catalyst, this reaction is giving high enantiomeric excess for the resulting epoxide. Okay, so this is the structure of L plus diethyl tartarate. Okay, diethyl tartarate is the diester of tartaric acid. Okay, so it's a 4 carbon species, 1 2 3 4 COAT. On the terminal carbon atoms the diester groups are there, and in between the between carbon atoms are having the hydroxy group. Okay, so this is L plus diethyl tartarate. This is the structure, and this molecule is acting as a chiral catalyst. Okay, and that's why the reaction is giving asymmetric epoxide product. Okay, now I am again telling you the reagents, 3 reagents we are using here. Tertiary butyl hydroperoxide is the oxidizing agent, which is source of oxygen in this case. Then titanium tetraisopropoxide is the transition metal catalyst, and L plus diethyl tartarate is the chiral ligand in this case. Okay, so what is important here? How that reaction is happening. Okay, so this is the case when we are aligning this allylic alcohol in such a way that the hydroxy group, okay, that is hydroxy group is at the top left in the plane, Suppose this is the carbon-carbon double bond, this is my left hand side. Okay, so if we treat this carbon-carbon double bond and let us say the substituent hydroxy group CH2OH at the top left of this molecule, then what happens when we are using L plus diethyl tartarate, the similar case in this example, L plus diethyl tartarate, in this case oxygen atom is delivered across this carbon-carbon double bond from the bottom face of the alkene, So this is a carbon-carbon double bond. Let us say this is CH2OH molecule. We can CH2OH side chain. Okay, CH2OH. This is the carbon-carbon double bond. So it has let us say like this CH2OH. Okay, vertical CH2OH. So this is top face and this is bottom face. Top face which is in front of you, and this is bottom face, or it is away from the observer. So you are the observer. Okay, so what is happening here? When we are using L plus diethyl tartarate, then oxygen atom is delivered from the bottom face of the carbon-carbon double bond. So this is carbon-carbon double bond, bottom face of the carbon-carbon double bond is this one. Okay, so oxygen atom is delivered from this side. And when we are using D minus diethyl tartarate, then oxygen atom is delivered from the top face of the carbon-carbon double bond. So this is carbon-carbon double bond, and this is the top face, let us say. So oxygen atom is delivered from the top face. Okay, and when it is delivered from the top face, we are getting beta epoxide. Beta epoxide means, what is my beta epoxide? Beta epoxide means the situation is like this. Oxygen atom in a 3-membered ring is above the plane. It is in the above the plane. So this is R group is there, and this is CH2OH. So this is the type of product that we are getting. So this is beta epoxide. Beta epoxide is we are getting from the, when we are using, only change, all these 2 reagents are remaining same, only the change is L plus diethyl tartarate and D minus diethyl tartarate. Okay, so beta epoxide we are getting, and when we are using L plus diethyl tartarate, we are getting alpha epoxide. So what is the case here? CH2OH. Okay, and here so this is the case. Top face, bottom face of the carbon-carbon double bond. Okay, so these things you have to keep in mind while solving the problems, or while studying this asymmetric epoxidation, Sharpless asymmetric epoxidation. So plus DET, L plus DET, alpha epoxide bottom phase, and a D minus DET, beta epoxide top phase. Okay, now how actual this happens, that is very critical when this titanium forms a complex. A critical complex is formed by this titanium tetraisopropyl with this carbon-carbon double bond and with the help of this diethyl tartarate along with this tetrabutyl hydroperoxide. And when allyl alcohols get closer, it comes closer to this complex formed by this transition metal titanium. Okay, then the alignment is done in such a way that the oxygen atom which is delivered from the oxygen atom which is delivered from this tetrabutyl hydroperoxide is from the bottom phase and from the top phase in that complex. Okay, so in this video lecture it is it cannot be explained properly due to these limitations. Okay, so whenever we will meet, then we can see how that can be happen. Okay, now let us see the numerical problems based on this. Problems of chemical reactions based on this asymmetric epoxidation. Okay, so this asymmetric epoxidation is very useful for the synthetic point of view, synthetic chemistry point of view. Let us have some reactions. So we have a chemical reaction, hydroxy carbon-carbon double bond. This is starting material. This R is having a larger group, a larger substituent. For sake of convenience, I have only written here R, and meanwhile when we are going to see the reaction sequence in detail, then we will take this R, actual R group, what will it will be. Then tertiary butyl hydroperoxide, OOH, then catalyst, transition metal catalyst, titanium tetraisopropyl OIPR 4 times, titanium tetraisopropyl, and the catalyst chiral ligand is D minus DET, D minus DET. So now we know that D minus diethyl tartarate is giving the beta epoxide, and hence our product in this case is OH. No harm to this side chain, nothing will happen. O, this is R. So we are getting this molecule, this R is nothing but a very large group, it is C10H21. Okay, and now next step is PDC. So what is PDC? Pyridinium dichromate. Okay, and this PDC is oxidizing agent. So this is primary alcohol, no harm to this epoxide. Primary alcohol is get converted to limited oxidation step is there. So alcohol is oxidized to aldehyde. So we are getting CHO, simply writing CHO in full structure. Okay, CHO, CH2OH is get converted to CHO. Okay, this is directly attached to epoxide, and this is R group, actually R group. Now this is epoxide, and next step is the Wittig reaction. So when we have a Wittig reagent like this, isopropyl group is there, CH2, then carbon-carbon double bond with PPS3. So this is Wittig reagent, triphenylphosphine, and this is carbon side chain. Okay, so we know that Wittig reagent. What is the Wittig reaction? There is a formation of carbon-carbon double bond, that is alkene, with the help of an carbonyl group, and then this Wittig reagent. Okay, so what will be the product? which is beta, this R side chain, okay, and here this carbon is forming a carbon-carbon double bond. Simply write, remove this ppsr group and simply write here this carbon. Okay, so what will be the side chain? CH2 carbon, and this is carbon-carbon double bond. Okay, so this is the product of this reaction. Okay, then the next step is the H2 in presence of catalyst, nickel or platinum or palladium. So what will happen? This is a carbon-carbon double bond, unsaturation is present, it will get reduced, it will get hydrogenated, and we are getting here the final product. It is nothing but CH2 1 2 3 4. Okay, this is epoxide. This is epoxide, 3-membered ring, 1 2 3 4, and then isopropyl group, 1 2 3 4 isopropyl group. Okay, our side chain is okay, and this R is having C10S22. Now this correct side chain is 1 2 3 4 5 6 7 8 9 10. Okay, so a complete straight chain of 10 alkyl groups, 10 carbon atoms, 1 2 3 4 5 6 7 8 9 10. So this is the side chain C10S22, 1 2 3 4 5 6 7 8 9 10. Okay, over. So this is the final structure. And what is this molecule? This is disparlure. So this is the final molecule, and this final molecule can be prepared by using this strategy known as Sharpless asymmetric epoxidation. Okay, I think you got it. Then next example is preparation of propranolol by using the Sharpless asymmetric strategy. Sharpless asymmetric epoxidation can be used for the preparation of propranolol. And this propranolol is chiral beta blocker. Propranolol is a chiral beta blocker. Chiral beta blocker reagent is there, and this can be synthesized by using a Sharpless asymmetric epoxidation. The final molecule is like this, that we have to synthesize. Okay, so O CH2 hydroxy group, then CH2 NH IPR. So this is isopropyl group is attached to this nitrogen atom. Okay, so this is the final molecule that we have to synthesize. Okay, this is what propranolol molecule. Now when we do a retrosynthesis of this molecule by breaking this CN bond, carbon nitrogen bond, then what will happen? We are getting this synthetic equivalent of this will be isopropyl alcohol. So that is NH2 IPR, isopropyl alcohol. So R is isopropylamine we are getting, and this is 1 2 3 membered epoxide will be there. So synthetic equivalent of this will be epoxide. O CH2 CH O. So this synthetic equivalent can be obtained by breaking this carbon nitrogen single bond. Okay, so this plus this we are getting this. Now how to prepare this molecule? Now again we have this carbon oxygen double bond, carbon oxygen single bond. Break this carbon oxygen single bond, disconnection approach. Okay, so what we are getting? We are getting this naphthoxide, alpha naphthoxide ion plus plus this alpha epoxide plus this alpha epoxide. Okay, and this alpha epoxide OH, okay, plus this alpha epoxide. Now how we can prepare this alpha epoxide? By a allylic alcohol. So this is OH CH2, this is allylic alcohol. So let us see here, this is our target molecule known as propranolol. This propranolol is a very effective chiral beta blocker, okay, that we have to synthesize. Now when we are look carefully this molecule, then this is a carbon nitrogen single bond. We can disconnect this, and therefore we are getting here this as a starting material and isopropylamine as a simple molecule. Okay, again we are doing retrosynthesis for this carbon oxygen single bond, and we are getting this naphthoxide ion plus this allyl plus this epoxide. Okay, and we are making this, we can make this alpha epoxide from the allyl alcohol. So Sharpless has succeeded for making this molecule, that is propranolol, by using his own strategy, that is known as Sharpless asymmetric epoxidation. But directly starting with this allyl alcohol, he has started his reaction with silylated carbon to this carbon-carbon double bond, and that's why the actual synthesis which is done by us, which is done by this Sharpless is like this. This is allyl alcohol SiMe3. Okay, so this is silylated carbon, silylated olefinic carbon he has used, okay, for the actual synthesis. Instead of simple taking allyl alcohol, he has taken silylated carbon allyl alcohol. Okay, then tertiary butyl hydroperoxide OOH, then titanium tetra isopropoxide, and D minus diethyl tartarate. So as D minus diethyl tartarate is there, so beta epoxidation takes place, and we are getting OH SiMe3 O. So we are getting this with high enantiomeric excess. Now what happened? The hydroxy group is having primary alcohol group having open hydroxy group. Okay, then that hydroxy group is methylated by using methyl chloride, and second one is, when it is methylated, then second one is hydroxy group is get converted to OMS, OH is get converted to OMS, that is methylate group is there, okay, on oxygen atom. So this is a good living group, so that's why this is the strategy that he has used, good living group. And then when we are using nucleophile such as AR, this is the nucleophile AR O minus Na plus, sodium naphthoxide, okay, sodium naphthoxide when we are using, then it attacks from the opposite side of this, and that's why this epoxide is get inverted, and that's why the molecule will become like this, O CH2 this epoxide is get inverted SiMe3. Okay, so all these remaining things will remain as it is. Okay, then what will happen next is tetrabutyl ammonium chloride F minus, tetrabutyl ammonium chloride. So what this reagent is useful for the demethylation. Demethylation is done by tetrabutyl ammonium chloride. In this, F minus is the nucleophile which is essential for the desilylation. Okay, and when we are using this reagent, it simply delivers hydrogen atom at this place, and that's why we have this naphthyl ring O CH2 okay, we have only simple this. Okay, and now when we are using another nucleophile, that is isopropylamine, that is NH2 isopropyl group. This NH2 lone pair can attack on this, and epoxide ring opening takes place, and we are getting this naphthyl ring, oxygen CH2, hydroxy is alpha, then CH2, and this carbon, this methylene group is attached to nitrogen, which is having NH isopropyl. So this is our target molecule that we have prepared. This is a structure of propranolol that is prepared by the Sharpless by using his own strategy, Sharpless asymmetric epoxidation. Okay, then the next example is another example of this Sharpless asymmetric epoxidation, and in that example, instead of using diethyl tartarate, they have used diisopropyl tartarate. So diisopropyl tartarate is the diester of isopropyl alcohol and tartaric acid. Okay, so DET is replaced by DIPT, diisopropyl tartarate. This is the only difference. Okay, remaining things will remain as it is. So the reaction is like this: fluoro, this is allyl alcohol. Okay, CH2 double bond CH, CH double bond CS, CH2OH. Now when we are using D minus DIPT, then tertiary butyl hydroperoxide and titanium tetraisopropoxide. Okay, so what will be the reaction? Only change is that we are getting here D minus, so that's why we are getting beta. Yes, we are getting beta epoxide here. So oxygen is delivered from the top phase. Okay, then CH2OH. Now here this is the epoxide ring. Now on this epoxide ring, the nucleophile is attacking, and the nucleophile that we are using here is this one, F nitrogen, carbon oxygen double bond dimethyl group. This is NLi. This is the nucleophile, and this nitrogen lithium bond is a nucleophilic nature, so I am writing only Nu minus. So nucleophile is attacking on this epoxide carbon, and it get open like this. Okay, so that's why we are getting here, we are getting this ring, fluorine, nitrogen, carbon oxygen double bond dimethyl group, and this nitrogen is get attached to this carbon. So nucleophile is get attacking on this, so this hydroxy group, which is beta, is this bond will broken, and this hydroxy group is attached to this carbon, CH2OH. Then this is attached to aromatic ring, fluorine. Okay, so this is backside attack, so that's why we can show this by a wedge line. So this is the case. Okay, now this tosyl primary hydroxy group is there, so we can use tosyl chloride. So when tosyl chloride is used, so this primary hydroxy group is preferentially tosylated and we are getting OTS here. Okay, when we are getting OTS, this hydroxy group is get converted to a good leaving group, that is OTS. And now when we are using base, this base is abstracting this proton, acidic proton, and it is attacking on this carbon, leaving out this OTS as a good leaving group. So my product will be, in that case, F nitrogen dimethyl carbon carbon oxygen double bond, then OH, sorry, so the another epoxide will be formed here, which is beta. Okay, and this is get attached to the aromatic ring. Okay, so this is the situation. Sorry, yes, this is the situation. Now here our simple methylamine MENS2, methylamine, a primary amine, can attack on this epoxide carbon and this ring can be opened. Okay, and we are getting here, we are getting fluorine nitrogen dimethyl group, carbonyl, nitrogen is alpha bonding to this carbon. Okay, and this hydroxy is now beta, and CH2 NHMe, CH2 NHMe. Okay, and this carbon is attached to the another aromatic side chain. Okay, so this is our final product. Okay, so such type of reaction can be asked in your examination. Okay, so what is there, what is important here? The important part is use of this chiral ligand, that is diisopropyl tartarate, which is D minus. Okay, so that's why epoxidation takes place from the beta side, that is from above the plane, that is from top face of the carbon-carbon double bond, and this is the reaction sequence you can judge. Okay, so this is the first type of epoxidation, that is known as Sharpless asymmetric epoxidation. Now second type of epoxidation that we are going to see, and that is manganese catalyzed Jacobson asymmetric epoxidation. Manganese catalyzed Jacobson manganese saline, this is known as manganese saline. Second, manganese saline, this is the short name of that chiral catalyst, manganese saline Jacobson asymmetric epoxidation. Manganese saline Jacobson asymmetric epoxidation. Okay, the things are different in this case. We are going to see that one. Okay, the main thing or the main importance part of this Jacobson asymmetric epoxidation, that we can do epoxidation of any simple alkene. We can do epoxidation of any simple alkene. There is no any limitation for the allylic alcohol. Okay, so what is here, this saline catalyst can be made by using derivative of salicylaldehyde. So this saline catalyst can be made or can be prepared by using derivative of salicylaldehyde. So what is salicylaldehyde? We know that this is CHO, this is hydroxy. For sake of convenience, we have taken that molecule as a horizontal, CHO. This is salicylaldehyde, okay, and tertiary butyl groups are attached to this aromatic ring at the third and fifth carbon atom. So that's why this is the derivative of salicylaldehyde, and we can prepare this salicylaldehyde by using a chiral cyclohexane derivative. So this is diamine NH2, and this is also NH2, but there is a difference. So this NH2 group is above the plane and this NH2 group is below the plane, okay, so they are anti to each other. And K2CO3 base is used, potassium carbonate, water and ethanol and some heating, okay. So what is happening here? The two molecules of this derivative of salicylaldehyde, one molecule of this diamine, they are forming such a complex or such reagent is formed that is known as chiral reagent, and that is found between these two, okay, and that we are going to write here. Simple NH2 carbonyl coupling is there and cheap base is formed between this is hydrogen, this is tertiary butyl group here, again tertiary butyl group is there, okay, this is hydroxy, now OH, nitrogen, carbon carbon double bond, and all remain as it is, okay. So this is the important stereochemistry, they are anti to each other, okay. Then aromatic ring, so dimer of this salicylaldehyde derivative, this is tertiary butyl group, this is also tertiary butyl group, and here it is hydroxy, okay. So a cavity is generally formed between the reaction between two molecules of this 1,2 dimer and one molecule of this diamine, okay. And when we treat this moiety with MnOAc, that is manganese acetate, okay, in which manganese is in plus 2 oxidation state dihydrate, and sodium chloride water, okay. So what will happen? This is transition metal catalyst, that is manganese, it is get flanked between this cavity and it is forming a catalyst known as stable manganese silane catalyst. I am writing directly here because it is very time consuming, okay. It is forming like this, Mn, this hydroxy will be lost, hydrogen atom will be lost, and it is forming 1, 2, 3, 4 and this Cl. This Cl is coming from the NaCl, okay. So this manganese in pentavalent, this is pentavalent manganese silane. Silane is the short form of derivative of salicylaldehyde. So manganese silane, this stable complex is acting as a chiral catalyst. Chiral catalyst is used for the or this chiral reagent, let us say chiral reagent is formed between this manganese acetate and this molecule, okay. And this is used for the asymmetric, Jacobson asymmetric epoxidation reaction. Now how that reaction is going to happen, let us see, okay. We have indene, this is the indene, 6-membered aromatic ring, that is benzene is get fused with the 5-membered ring with a carbon carbon double bond, okay. This is indene, and when we do Jacobson asymmetric epoxidation reaction, okay, the reagents are Mn silane manganese silane and sodium chloride, water. So these are the reagents for the Jacobson asymmetric epoxidation reaction. So the products are we are getting enantiomerical excess of this alpha epoxide. Okay, only change is that carbon carbon double bond is get converted to carbon oxygen, carbon oxygen, that is 3-membered epoxide ring is formed, and this compound we are getting 99% enantiomeric excess. See the enantiomer selectivity, 99% enantiomeric excess we are getting. Okay, and we are getting here alpha epoxide. That is, oxygen is coming from the bottom face of the carbon carbon double bond. Okay, so these are the two examples of, or two methods of the asymmetric epoxidation, known as Sharpless, and second one is Jacobson. Okay, so thank you very much for seeing this video. Have a nice day.